Sure. Let me first start recording. So this is Thursday of the 7th week. So I guess it's lecture number 14. And we have a question on the homework. I'm gonna load up Sapling so that I can see which question you're referring to. Which chapter?
Chapter 15.
Okay, 15, question number 2. So let me find it. Okay, so email, login. Here we go. Okay. So let me share the screen. Why did the exam destroy you? That I can't say. I don't know. Why did the exam destroy you? You should have destroyed the exam. That's what should have happened. Chapter 15, question number 2. You tried. I know. All right, question number 2. Let's illustrate the idea of a sampling distribution in the case of a very small sample from a very small population. The population is the scores of 10 students on an exam. So students 1 through 10, and there are those scores. The parameter of interest is the mean score mu in this population. Of course, if I really wanted the mean score mu, I can just average them. Just add up to 10 and divide by 10, and you get 69.4 apparently. All right, because this is the entire population. Because it's the entire population, we label the mean by the Greek letter mu, which is the population mean, the parameter. It's about the entire population. But for this simplified example, I'm taking an SRS of 4 students drawn from the population. Now, because my sample size is so small, the only time I know that this will be a normal sampling distribution is if the original one is normal. But with only 10 scores, it's very hard to determine whether or not it's normal. So let's see what they want us to do here. Because there are 10 students, a single random digit from table B chooses 1 student for the sample. So if we go to table B, random digits, so we see that if we just do the very first line, 1, 9, 2, 2, student 1, student 9, student 2, we'll repeat, skip him, student 3. So if we use this one, we can use student 1, 9, 2, and 3. So let's see what they want. Make a histogram of these 10 scores using bins whose endpoints are 40, 50, 60, 70, and 80. Is it skewed left or skewed right? Well, let's quickly try to do this right here on the thing. So here's 40, here's 50, here's 60, here's 70, and here's 80. So the 40 to 50 bin, we have none. The 50 to 60 bin, we have 1, 2. So it'll be a height of 2. Oh, wrong one. It'll be a height. Oh, come on. It'll be a height of 2, 50 to 60. So 0, 1, 0, 2. 60 to 70, we have 1, 2, 3. And 70 to 80, we have 1, 2, 3. And I don't know why they said 40 to 80. We really got to go all the way to 90 because there are some very good students here. 1, 2. Okay, so is the histogram symmetric, skewed left, or skewed right? Well, if you look right here, it is a perfect copy to the left and to the right, so it is certainly symmetric. It's kind of weird they wanted 40. They should have said 90. I don't know. That's probably a typo on their end. Do you see why it makes no sense, 40, but it should be 90? That's just based upon the data. Anywho. Label the students 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Use the first digits in row 116. Well, I use 101, but they want me to use 116. So we're going to use student 1, student 4, skip him, student 5, 9, 1, 4, 5, and 9. So the first score is 86, 55, 72, 75. And what does their mean? What's the mean of them? Well, you add them up and divide by 4, and you get 72. Does that make sense so far?
Yes, thank you, Professor.
Okay, so which part?
Can you repeat it one more time?
Which part?
The second part. I'm still unsure. So if you could scroll up a bit. Yeah, for the mean, 69.4. Was that the mean of the score?
Yeah, I mean, they want us to, right here it says, I'll underline it so you can see what I'm pointing at. It says the parameter of interest is the mean score mu, the average score, right? So these numbers, right? We add them up and divide by 10.
That's where I got confused because it said the population and I thought that was referring to the students, the number of students.
Well, it is. The population is the scores of the 10 students on the exam. So it's not technically the students, it's their scores that's technically the population. Yeah, because the population are the numbers that you're looking at, not the individual. Well, I mean, that's a semantic difference. But if you're going to do math, you got to be working with numbers. So when they're asking for a value of something, you know, it's not the people themselves, it's their scores. Does that make sense?
Yeah, thank you.
All right, and then repeat this process 9 more times. Well, Jesus. Okay, repeat this process 9 more times using the first digits in rows 117 to 125 of table B. So after I finished with the first one, I would then go to 117 and use student 3, 8, 1, and 6. And then student 7, 3, 1, and 9, and 9, 5, 8, and 7. Remember, we skipped this one. We already did them. 3, 5, 4, and 7, and so on. So we do this 10 more times. And I can't answer this question without actually doing it. But essentially what you want to do is get your 10 X bars from each of those and do the same thing. Make a histogram of your 10 X bars with 40 to 80 or possibly 90 as your endpoints. And what you should see is that the sampling distribution is tighter, because as the sample size goes up, we know that the width goes down. So without even doing it, the histogram of the 10 sample means is less spread out than the population histogram, and its center is greater than mu. Now, I would think it will be equal to mu, but remember, its expected value is equal. You can't actually expect the actual mean to be the same. I would have to do the math, but if someone said, don't do the math, just guess, I certainly would have guessed the first one. Certainly not the second or the fourth, because the histogram should be less spread out as the sample size goes up, not more spread out. But I would expect its center to equal to mu, but then again, it's an actual sample. So, you know, the math is what the math is, and just it turned out to be greater, assuming that they're correct, which there's no reason why I would believe otherwise. So does that make sense for that one? Any questions?
Thank you, Professor.
You're welcome. Any other questions on the homework? The last question, the population equals a student with a score, I guess. I mean, again, it's a semantic argument. Is the population the people, or is the population the numbers? You know, I don't know. It's. I guess I'm sure there's a technical answer to that question, but as far as we're concerned, it's the math, it's the numbers that counts. It's the values, the weights, the heights, the scores, the IQs. Is there a short way of doing this, or do we actually have to do that 10 more times? Well, you don't got to do it 10 more times. only 9 more times. So that's a shorter way of doing it. It'll save you an extra 19 seconds of your life. But no, for that particular question, I don't see a shorter way of doing it. Sorry, I don't make the questions, I just assign them. Just a messenger, so don't blame me. Stats is mega dumb. Wow, okay. Well, I don't know if that's necessarily true, but I yeah, that's just, you're basically saying that everything I've devoted my entire life to is just dumb. So, I don't really like that too much, but I don't care. I think most an IOP, the person that said that is capping. I don't know what these things mean, guys. I'm too old. You guys are making me feel old. Why do you do that? What the hell does capping mean? I never cap on God. I don't know what you guys are talking about. Okay. Anyways, so let's go back to the ebook. We were, I don't even know where the hell we were. I can't keep anything straight anymore. I think the last thing we did was chapter 16, right? Or part of 16, correct? Yes, no, maybe so. Anyone?
Yes.
Yeah. Did we start with did you record that class? I record every class. The problem is that for some reason lately, when I try to upload these Zoom meetings, it takes hours and hours to upload. And then at the end, and when I'm talking about hours, I mean like 5 or 6 hours to upload a class. And then at the end, half the time it says error, do it again. So it's just been very frustrating on my end lately, and I don't know how to fix that. Someone recommended that I remove some of the older Zoom meetings, and it might be a space issue, but I didn't want to do that without asking anyone because you guys might still want them. So I haven't made that call yet. Yeah, so I'm not. I don't want to do it. I don't. Can you place them in CSUN box? I don't know what that means. What is CSUN? I don't know. Shows them on 16. Shows I am on 16.2. Oh, you tell me where I am. Okay. I don't know what that is. If you want to let me know, give me some options. That'd be wonderful, and I'd be more than happy to try anything because lately just uploading them has not been working. All right. So back to the thing. So 16.2. 16.2 confidence intervals, margin of error. So let's just recap a little bit what we've been working with. When it comes to this thing, this confidence intervals, which are very important. CSUN Box is a video recording program that uses Canvas. Oh, well, if you can, oh, it's an archive for all interests. If you can give me send me an email if you don't mind on some more. Well, don't do it right now, but actually, I don't want to trouble you. I mean, that's on my end. That shouldn't be your responsibility. All right. So margin of errors and confidence level. So we talked about this fact that when you have a population, the population has some value of a parameter that is usually unknown. The most common ones that I think of are heights, weights, scores, things of that nature. You have a lot of people, 1 million people took the SAT. What's the average score type thing? Now, in that case, it's not hard to figure it out because everyone who took the SAT is in the system. You just have the computer do it and you pop out the average and you don't got to do a sample. But things like the average height, the average weight, the average salary, the average this, the average that, these are things that are much more difficult to ascertain by looking at everything. So we take a sample. And when you take the sample gives you an estimate. Usually if I'm sampling, if I want the mean of a population, I take the sample mean. It's a wonderful estimate to use. Probably the best estimate, definitely the best estimate. But with that estimate comes the recognition that just because my estimate is here doesn't mean that I'm discounting any other possibility. There's a range around that estimate for which I can be fairly confident the true value is somewhere in that range. And this is the idea of a confidence interval where you have the estimate plus or minus a little bit. So you plus a little bit or you minus a little bit. You go in both directions and it creates an interval. And there's three factors that determine the size of the interval. One is how confident you want to be, the confidence level. The typical confidence levels that we use are 90%, 95%, and 99%. I guess that's in the next section, so we'll see that in a minute. This particular box talks about a 95% confidence interval, but you can have confidence of any amount. So one is the confidence level. That dictates how wide the interval is going to be. The second is your sample size. The larger the sample size, the more confident you are in your answer, the tighter it's going to be. So a larger sample size will make the interval smaller, all else being equal. And then the third one is the actual standard deviation of the population. Because if the population itself has a very big spread, then your confidence interval is going to have a fairly large spread. And if the population has a very small spread, then the confidence interval will correspondingly have a very small spread. So these are the three things that play a role in the margin of error. It's the plus or minus part. Your estimate plus or minus the margin of error. We did all this last time. I think we finished 16.2 last time, did we not? Is this all new, or is this, I never remember. I leave it up to you guys to remember where I am. Anyone?
I think we did go over it, and then we went over how to do it and crunch it.
Okay, good, good. So let's go to 16.3, where we have the actual formula, which we did last time. So here we have the three confidence levels that are the most typical, the ones that appear the most often in problems. The 90%, 95%, and 99% confidence levels. And I think we did this before. I'm pretty sure I did this twice, which means your class and the other class. And I described where these numbers come from. So for 90% confidence, our critical value Z star is 1.645. 95% confident it's bigger. 99% confident it's even bigger. And those three play a role here in the formula for the confidence interval for a population mean. X bar is your sample average, plus or minus Z star. Z star is one of these three numbers, assuming that we're going to use one of these three confidence levels, times the spread of the population. Again, this formula assumes that we know the spread of the population. So right over here inside the box, you see the extremely important known standard deviation sigma. If you do not know sigma, you can't use this formula. We use a different formula. So when you're doing a problem on a homework, on a test, and you have to decide which formula to use, you got to look at all the information. It's got to be an SRS. It's got to come from a normal population. The mean itself is unknown. That's what we're looking for. And sigma is known. Then they got to give you the confidence level. So they got to give you n, the sample size. They have to give you sigma. They have to give you the confidence level. From that, I can calculate the margin of error. And either they give you X bar or they give you the data itself from which you can find X bar. But they got to give you enough to actually solve this problem. Otherwise, you can't really do anything. So confidence intervals of 4 steps. Identify the parameter, choose a level of confidence, select the type of confidence interval. Again, at this point, we only have one. And then make sure the conditions are satisfied. It's got to be an SRS. It's got to come from a normal population. You have to know sigma, and then calculate the confidence interval. Okay, and as we go through the next couple of chapters, we're going to see that there's other situations where you don't know this, or you don't know that, or you know this instead, and we're going to come up with different formulas for different confidence intervals. And I think we did this one last time. So does that make sense so far? Any questions? I think that's all review. I think that's all review. And I think we did this as well. Pretty sure we finished the chapter. Did we not? I think we did this example here. If not, we talked about all of this. And we're going to do more. This is just the basics of confidence intervals. as we see in the next couple chapters after 17 and 16 and 17, we're going to actually spend a few chapters on just confidence intervals. So right now we're just doing the basics. So let's move on to chapter 17, which is the basics of tests of significance, also called hypothesis testing. Hypothesis testing is a little more challenging than confidence intervals. Gives people a lot of conniptions. I can imagine getting a lot of texts where confidence intervals are okay, but hypothesis testings are going to destroy you, things of that nature. So let's talk about what a hypothesis test is. Suppose that you go to the store to buy, let's say you go to Subway. This actually occurred, like I remember reading an article about this like last year. Oh, someone says something. What do they say? So I'm very confused on confidence intervals. Okay, so what are you confused about? So let's, before we move on, tell me what you're confused about so I can answer it. The whole thing, to be honest, that's a little too vague. I need a little more specifics on exactly what you're not sure about. Don't understand the table you used. Which table are you referring to? This one? The last example. You mean this table here? Well, these are just the numbers that you use for different levels of confidence. So if I tell you that you're dealing with a 90% confidence interval, then the Z star that appears in your formula, you're just going to use 1.645. And if I tell you that you're using 95% confidence, then the Z star that appears in your formula, you're just going to be 1.96. And if I tell you that you use 99%, just 2.576. This, I didn't derive this equation, nor am I going to derive this equation. This equation I'm just giving you as fact. I'm telling you this is the equation for the situation where you're looking for the mean from a normal population and you know sigma. In that situation, this is the formula. Without explanation for where the formula comes from. That is the formula. So the four things you need to compute the confidence interval are: one, X bar. That is your sample average. So you have a sample and you compute the average, right? You add them all up and divide by how many you have. Can you go over how to do it on Cruncher one more time? Yeah, I can do that. Okay, so X bar is your average. Z star comes directly from the confidence. Sigma is given and is given. So given, confidence level given, therefore you can get this because one automatically implies the other. And then you have X bar. So someone said, can we do an example? So let's go do an example. Check your skills. X bar, not X. X bar is the sample mean. Let's see. Well, first let me get rid of that thing. Okay, let's do this one right here. Use the following information for exercises 16.12 to 16.14. A laboratory scale is known to have a standard deviation of sigma equals 0.001 gram in repeated weighings. Scale readings in repeating weighings are normally distributed with mean equal to the true weight of the specimen. Three weighings of a specimen on the scale are 3.412, 3.416, and 3.414. Compute a 95% confidence interval for the true weight. I will do it on Crunch It in 2 minutes, but I want to give you the chance to write out what you think it is. Go ahead. If you have no idea how to do it, that's one thing. But hopefully you do, so you can. Not sure is fine. Not sure is fine. Not sure either, not sure. Okay, well, I guess we'll start by calculating X bar. Don't even need a calculator for that one. So someone tell me, what is X bar for this problem? Or more specifically, how do I find X bar for this problem?
3.414.
Sorry, say it again.
3.414.
And can you tell me where you got that from?
I got that from the population. I added the 3 numbers and then divided by 3.
So not the population, from the sample.
Or the sample.
Okay, so X bar is the sample average. You take the 3 samples and the three numbers you get, and you add them and divide by 3. So X bar equals 3.414. What is
that from the specimen?
I'm sorry?
Is that from where it says the 3 wangs?
Yeah, this my sample is a sample of 3. I got a value of 3.412, a value of 3.416, and a value of 3.414. So X bar, you just add them up and divide by how many you have.
All right, thank you.
Does that make sense?
Yeah.
Okay. Now, let's see. Is anyone not sure about what I just did? 3.414. What's sigma for this problem?
0.001.
0.001. They gave that to me. What's n for this problem?
3.
3 samples, or 1 sample of 3. And what is my confidence level for this problem?
That's what you have to solve for.
Not for number 12. They tell me what my confidence level is.
Oh, I'm looking at the wrong thing.
99.9.
No, 99.9 is up by 11. We're down by 12. 95%.
Oh,
Right? The 99.9 is up top. We're in question number 12. Right? It says use the following information for 12 through 14. So we're number 12. So a 95% confidence level. So C is 95%. So what is my Z star going to be? What is my Z star?
We have to refer back to the table.
Oh, I'm sure you wrote it down like I asked. So that should be an issue, right?
I forgot it.
X bar plus or minus.
1.960.
1.960. All right. So these are the 5 values for this problem. X bar, which we calculate by adding them up and divide by how many we have. Sigma because they gave it, N because they gave it, C because they gave it, and Z star because whenever C is 95%, Z star is always 1.960. So what is the formula for the confidence interval? The generic formula first, before we actually plug in numbers. What's the generic formula for the confidence interval?
X bar plus minus Z star. I'm assuming times sigma over square root of n.
Right, X bar plus or minus Z star sigma over the square root of n. All 4 of which we have, which means we can write it down. 3.414 plus or minus 1.960 times 0.001 over the square root of 3. So 1.96 times 0.001 divided by the square root of 3. So I get 3.414 plus or minus what number? What does your calculator give you, which hopefully you're all doing? Oh, someone
Yeah.
wrote something, 3.413 to 3.415. Yeah, I guess if you round to third decimal, that is correct. But look at your answers A, B, and C. So they're not actually asking for the left endpoint and the right endpoint like you gave me. They're asking for the center plus or minus margin of error version. So while you're correct, it's not technically what they were asking for. So is it A, B, or C?
It's A.
It is A, and that's just plugging into the calculator. So if I do 3.414 minus what I get from part A, I get 3.41287 approximately. And if I do 3.414 plus what I get from part A, didn't like that one. 3.414 plus what I get from part A, it gives me 3.41513. So this is my confidence interval in two different forms. One is center plus or minus blank, and one is left edge, right edge. Now, let's do it on Crunch It. What are the three confidence intervals? What do you mean, what are the three confidence intervals? I'm not sure what you mean by that. Oh, how do you find 1.96? That was,
Table.
I mean, that was right here. 95%, 1.96. I mean, this table, I mean, just write it down. Right? 90%, 1.645. 95%, 1.96. 99%, 2.576. So, where were we? So let's go back here and let's go to Crunch It. So they put in the three values. So we go to statistics. We go to Z star, Z, it's one sample. We're looking for a confidence interval, and we're looking for a 95% confidence interval. We do have to provide sigma 0.001. The sample is the weight sample. So we got to plug that in too, and we calculate, and it gives me 3.4. Oh, that's what you gave me in your message, 3.413 to 3.415. So does that make sense? Yes.
Which part of the top did you click? The
Here,
to get, yeah.
I did statistics. I did Z. I did one sample. And then I clicked, this is a hypothesis test, which is we're going to do in a few minutes. And this is confidence interval.
All right, thank you.
Okay. So the next question is, you want a 99% confidence interval for the true weight of the specimen. So we already have the 95% confidence interval. Now you want a 99% confidence interval. The margin of error for this interval will be smaller than the 95%, greater than the 95%, or about the same as the margin of error for the 95%. So why don't we go ahead and, we haven't done this in a while. Let's go ahead in the chat box. On the count of 5, it will be A, B, or C. 1, 2, 3, 4, 5. Wow, he was quick. Greater, that's not A, B, or C, just A, B, or C. So I can see, it's easier for me to see. Otherwise I gotta go back and I gotta see which is greater, I don't know, A, B, or C. Someone said, can I ask a question? When they say, can I ask, what is the answer actually? Oh, what is the answer actually telling us? Oh, that's deep. So give me a second. When I see an A, I see lots of B's. I see a not sure. I saw a C. And mostly B's. Okay, so first let me answer the question about what is the confidence interval telling us? So this confidence interval that I calculated is telling us that I am 95% confident that the true mean that I cannot and will not ever know is between this number and this number. Could it be outside of that? Sure, but I'm 95% confident it's between 3.413 and 3.415. That's what a that's what a confidence interval is. How confident you are that you caught it. Now, if I want to be more confident that I caught it, just make the interval bigger. The bigger the interval, the more likely it is that it's in there, that you caught it. So if I go back to crunch it, and I say, oops, and I go back to crunch it, and I say, I don't want a 95% confidence interval. I want a 99% confidence interval. So you'll notice that it looks exactly the same. The 95% that we had before and the 99% that we had before looks exactly the same. And the reason is because we're not doing enough decimals to really see the difference. I don't know how to add decimals on crunch it, but luckily we don't have to rely upon crunch it, because luckily all I have to do is if I go back to section 16.3, I see that if I want 99% confidence instead of 95% confidence, I don't use 1.960, but rather I use 2.576. And when I use 2.576, that makes the numerator larger. So if I do it just to get a definitive answer, 2.576 times 0.001 divided by the square root of 3. Now it gives me plus or minus 0.00149. So it's really a tough question to answer because the margin of error is larger. However, it's so close to what it was before. I mean, the only difference is in the 10,000th place that it's really legitimate to say that C is correct as well. It's about the same. So it's saying the actual mean is between, well, no, it's not saying the actual mean is there. It's saying I'm 95% confident that it's there. You can't ever say where it is. If you knew where it was, we wouldn't need statistics. I am 95% confident it's between these two numbers. Could it be outside those two numbers? Yes. But I have a certain level of confidence that I caught it. And here's another sample, is weighted 8 times on this scale. The average weight is 4.1602 grams. And now we have a 99% confidence interval for the true weight of this specimen. So we're still using the same data that we did before up here, but now it's a new sample and it's weighed 8 times with an average weight of 4.1602. So take a couple minutes, please, and see if you can get that one. I'll give you a couple minutes to try it. All right, so let's see what we got. Are we multiplying the sigma by 8? We'll just go to your formula and put in every number in its appropriate spot. X bar, Z star, sigma, n. Don't memorize, this is what we do here, this is what we do there. Go back to your formula, plug things in. but they don't provide us with sigma or n. Yes, they do, right here. Well, first of all, they do provide you with sigma. They say it right there. Sigma equals 0.001. This is exercise 12 through 14. And then they do provide you with n. If you read the question, they might not say n equals, but they give you enough information to find it. So the generic formula is x bar plus or minus z star sigma over the square root of n. What is my x bar for this example?
4.1602.
They straight up gave me that one. Plus or minus. What's my z star for this example?
2.576.
2.576. What's my sigma for this example?
It's the same one, so it would be 0.001.
What's my n for this example?
8.
So I get 4.1602 plus or minus 2.576 times 0.001 over the square root of 8. Now it's just a matter of taking out my calculator. 2.576 times 0.001 divided by the square root of 8 is 0.00091. So my final answer is 4.1602 plus or minus 0.00091. If I do it on Crunch It, so cool that you can just link it. Oh, this is a different sample. So let's do a new one. Let's get rid of that old one. Let's get rid of this for a second. So, oh, so if I do Crunch It, is it going to give, uh-oh, can't do it on Crunch It. It keeps giving me the old numbers. Oh, well. Can't do it on, well, here, what if I hit weights? This is so cool. Modern technology. Oh, no wonder. They didn't give us the weights, right? What if I download them on Excel? Oh, no, that's the other 3. Interesting. Okay, well, it's not perfect, obviously. Clear. Okay, obviously not perfect. I don't need this. I don't need this. Okay, so let's do another one. Use the following information for exercises 15 through 18. The National Assessment of Educational Progress includes a mathematical test for 8th grade students. Scores in the test range from 0 to 500. Suppose to give the NAEP test to an SRS. Ooh, SRS, that's one of our conditions, so that's nice to see. An SRS of 2,500 8th graders from a large population in which the scores have a mean of mu equals 282 and a standard deviation of sigma equals 110. Obviously, the mean X bar is going to vary if you take repeated samples. The sampling distribution of X bar is approximately normal. How do I know that, by the way? They tell me that, but how do I know that?
Sample is greater than 30.
Yeah, the sample size is much greater than 30, right? It's 2,500. All right, the sample size is much greater than 30, so it's approximately normal. It has a mean of 282 because I know that the mean of the original population is equal to the mean of the sample population. Or someone's do it. Yeah, exactly. So the question now becomes, oh, that makes it easier. The question now becomes, what is its standard deviation? What is the standard deviation of the sampling distribution? So we learned that. How do I get the standard deviation of the sampling distribution?
Sigma over the square root of n.
Excellent. Sigma over the square root of n. In this case, n is 2,500. Sigma is 110. So 110 over the square root of 2,500, which is 50, gives me 2.2. Make sense? I hope. Okay. How do I? Yeah, there we go. Okay. Okay, so let's go back to sharing. And let's go now to chapter 17. Hopefully that cleared up the questions on 16. If not, you're more than welcome as always to come to my office hours. But we need to go ahead. So I really don't need to, but how do I do this? Okay. So hypothesis testing. So let's say you go out and you go to Subway. I don't know about you guys, but a couple of years ago they had this special for this some kind of oh, it's been so long I don't even remember what it was called, but it was so good. Like a barbecue chicken type thing. I don't know what it was, but it was so amazing. Maybe you guys know what I'm talking about. No, it's not $5 foot long. That's, I mean, no, I'm talking about like the taste. I forget what it was, but it was so good. Anyways, so you go to Subway and you buy a sandwich. You buy a foot long because, you know, no one in the right mind only gets a 6-inch because you want to have a lot, right? So you buy a foot long. And you're looking at this supposedly foot long. And you say, you know what? Luckily, I'm a math person, so I have my ruler on me. I'm going to measure this because I don't think this is a full 1 foot. And you take your ruler out and you see that really it's 11.5 inches long. And you say, I knew it. Subway is jipping me out of a 1/2 inch of food. So you say, you know what? I don't think Subway really gives foot-long sandwiches when they claim that they're giving foot-long sandwiches. I hypothesize that they're really giving us less. That wasn't it. That wasn't it. It wasn't a barbecue chicken sub. I forgot what it was, but it was, I don't know. I'll think of it because, you know, I don't forget food usually. But anyway, so Subway comes along and says, we hypothesize that our sandwiches, H0, that the average amongst our sandwiches are what's called a null hypothesis. The original hypothesis is that the mean is equal to 12. And you come along and you say, you know what? I have an alternative hypothesis, H1, that the mean is really less than 12. H0, mu is equal to 12. H1, mu is less than 12. The way hypothesis testing works, is that there's always this null hypothesis, this status quo hypothesis, this hypothesis of what the belief is that something H null, N-U-L-L, H null, the null hypothesis. This is the null hypothesis. The null hypothesis. And this here is the alternative hypothesis. Sometimes you'll see H0, this little sub-zero, H0, and you'll see HA for alternative. But some books use H1. It could be HA or H1. But you have the null hypothesis, H0, N-O-U-G-H-T, H0. And then you have the alternative hypothesis. So this is what the belief has been up until the experiment that you're performing. And this is the alternative hypothesis. This is the one that you come along and say, you know what? I don't think this is correct. I think this is correct. So what you do is you take a sample. and you compute your mean from the sample, and you base your decision on whether or not you will accept or you'll either reject the null hypothesis or you will not reject the null hypothesis, right? So suppose for example, that you take a sample and your mean is equal to 11.942. Now keep in mind that this is only a sample. Some are going to be bigger, some are going to be smaller. On average, the mean is supposed to be 12. If you get 11.942 as your sample average, would you say that the data supports the null hypothesis or that the data supports the alternative hypothesis?
The alternative.
Well, remember, this is only a sample, right? This is only a sample. Do you expect to get an actual value of 12 every sample that you take?
No.
No.
Probably not. So if my sample is somewhere in the vicinity of 12, and the next person's sample is 12.168, and the next person's sample is 12.014, right? It's not because it's less than 12, it's close to 12. It's not so far away from 12 that you would say, oh, come on, 12, come on. There's no way the average is really 12. I got 11.942. That's less than that's a 20th of an inch away from 12. No, it does not have to be exact. The question is, will you question the validity of the null hypothesis based upon your sample value? If you take your sample value and you say, I just can't wrap my head around this as being the true value when my sample gives me this, that's when we would reject the null hypothesis. But if you get an average, let's say you take an average of 100 things and you get 10.5 inches as your average. If you take 100 footlongs and the average of those 100, this isn't mu, this is X bar, my sample mean. That's my bad. I'm sorry about that. X bar. If your sample average is 10.5, 10.5 inches, would you then say the subway's claim is most likely not accurate? This is far enough away from 12. Yeah, in this case, I would probably reject the null hypothesis. Right? I would reject the null hypothesis. But here in the first example, it's not far enough away for me to reject the null hypothesis. So I would not reject the null hypothesis. In both cases, I phrase my answer in terms of rejecting or not rejecting the null hypothesis. I either reject the null hypothesis or I don't reject the null hypothesis. It's not a matter of rounding. It's a matter of how close it is to what you expect. If your value is close so that you have to recognize that in real life, there's always going to be variations, right? If my variations are such that I'm relatively close to the value that I expect, I'm not going to question it. But if my value is far away from the value that I expect, that's when I do start to question it. So there's a range of values where I reject the null hypothesis, and then there's a range of values where I do not reject the null hypothesis. So if it was 11, so here's the question, right? There's some number where I'm going to switch from rejecting the null hypothesis to not rejecting the null hypothesis. And it can't be a different number for everyone. You can't say, oh, for me it's 11, and for me it's 11.5, and for me it's this, and for me it's that. We have to have a very systematic way of calculating the exact number where we say, less than this, I will reject, not less than this, I will not reject. And we are going to calculate that number. It's not hard. It's actually very, very straightforward. Let me do an example from the book rather than my own made-up example here. So let's look at this example right here. Right, this is the example that we're, oh, epsilon delta, look at you with your calculus. So let's do this example here. It says diet colas use artificial sweeteners to avoid sugar. These sweeteners generally lose their sweetness over time. Manufacturers therefore test new colas for loss of sweetness before marketing them. Trained testers sip the cola along with drinks of standard sweetness and score the cola on a sweetness score of 1 to 10, with larger scores corresponding to greater sweetness. The cola is then stored for a month at high temperature to imitate the effect of 4-month storage. And then each taster tastes the cola again after storage. This is called a matched pairs experiment because you're tasting the same sample before and after. You're matching your before after. It's a matched pair experiment, which we'll get to later. So our data is the differences, the scores before minus the scores after. The bigger the difference, the bigger the loss of sweetness. Forget about math for a second. Do we understand what's going on here? Are there any questions about what's happening? Yes? No? I hope so. Right? It's just it's plain, it's straightforward. I don't know how you can actually train yourself, but the situation should not be very, we haven't done any math yet. The situation should be basically self-explanatory. So suppose we know that for any cola, the sweetness loss scores vary from taster to taster according to a normal distribution with a standard deviation sigma equals 1. Like the confidence intervals, you have to know sigma for this case, and it has to come from a normal distribution, okay? So here are the sweetness tests for the cola currently in the market as measured by 10 trained tasters. 1.6, 0.4, 0.5, all these numbers. Some of them with a negative sign, by the way, according to their scores, the sweetness actually went up after 4 months, right? So went down, went down, went down, went up, went down, went up, and so on. The average sweetness loss is given by the sample mean is x bar equals 0.3. So that on average, the 10 tasters found a very small loss of sweetness. Also, more than half of the tasters found a loss of sweetness. Loss, 3, 4, 5, 6. Is this data good evidence that the cola lost sweetness in storage? That's the question. Is there enough evidence? So in the language of hypothesis testing, I would say that my null hypothesis, the null hypothesis, is that nothing was lost, that the difference between before and after is 0. And my alternative hypothesis is that the loss was greater than 0. This is what I'm worried about, right? Did I lose too much sweetness in storage? Now, our value of x bar was 0.3. Is 0.3 close enough to 0? By the way, it's also 10 people in my sample, right? So my x bar was 0.3 and there's 10 people in my sample. The question is that enough evidence to suggest that the sweetness loss is not 0 or it is 0? Remember, we're only questioning whether it's 0 or not. We're either going to reject the null hypothesis or we're not going to reject the null hypothesis. So let's take a look at what Crunch It will tell us. If I go to Crunch It, hopefully it has all my data. So these are my 10 scores in Crunch It. So someone said it's close enough. Well, let's take a look. Let's go to statistics. We'll go to Z, one sample. This time we're going to do a hypothesis test. What is the mean under the null hypothesis? What does the null hypothesis claim the mean is?
0.
0.3?
No, this is the sample mean. The mean under the null hypothesis is that mu is equal to 0. That's what we're testing. This is the mean, assuming the null hypothesis is correct. This is my sample mean. And the question is from my sample mean, do I have evidence to reject or not reject this? Now, is this a one-sided? Is this a less than, greater than, or a two-sided alternative test? So we didn't talk about this, but it might be roughly self-explanatory. This is a greater than test. What are the three options? Mu is greater than 0, mu is less than 0, or what's another option in theory that I can do to do a test besides greater than or less than? Okay, Stephen Hawking, what do you say? No?
Can you say greater than or equal?
Well, you never want to do you never want to do or equal to, because the equal, I know that was horrible, I know. Because the equals is oh, he's dead. What does he care? All right, because the equal is what we're looking for, right? The equal is this. The alternative can't match the equal. So it's either greater than oh, anyway, it's either greater than, less than, or not equal to. And the three possibilities for an alternative are going to be greater than, less than, or not equal. Sometimes we care specifically, did it go up? Sometimes we care specifically, did it go down? And sometimes we care whether or not it's just is or is not equal, and we don't care if it goes up or goes down. So it's greater than, less than, or not equal to. So that's the two-sided if it's not equal to, but this one is not two-sided. Which one is our case? Anyone?
Greater?
Huh? It is greater than. This is a greater than hypothesis test. Well, someone said something. Welcome, Carly. You missed some good jokes. So, yeah, whatever. I thought they were funny. That's all that matters. So greater than. What's my standard deviation for this example? What's my standard deviation? Wow, Stephen Hawking, I don't think he's watching over me. Anyways, I apologize to Stephen, Professor Hawking, great man, great scientist. So not after that, he isn't. Oh, wow, that was horrible. Okay, so anyways, what's my standard deviation? They gave it to me in the problem. What was it? It's 1, okay. So sigma is equal to 1. My sample is the loss column. So I put my sample's loss column, and I'm doing a hypothesis test. Right? So let's see what crunch it says, shall we? When I calculate, so let's look at that. Let's ignore the details for now. And we have the null hypothesis that the population mean is 0. We have the alternative hypothesis that the population mean is greater than 0. We have n, which is our sample size. There's 10 in our sample. We have the sample mean, which was 0.3, and the deviation, which was 1. And then finally, we have these two values, which we'll get to later. Let's not worry about what they mean, okay? Always, we're not going to worry about how to compute them, but we are going to look at the p-value, which is the most important one. The p-value basically, essentially, is telling you this. If the null hypothesis were really true, there's a 17.14% chance that I would have gotten an outcome like this. If the null hypothesis were really true, there's a 17.14% chance that I would have gotten an outcome that is as far away from 0 as 0.3. Now, a 17% chance of something occurring. If it did occur, would you be like, what? That's crazy? Or would you say, okay, I didn't see that one coming, but not shocked by it? What's your answer to that? Which one is a 17% chance? Is that like a crazy occurrence? Or is that just an unlikely occurrence that if it happens, It happens regularly enough. It's not, yeah, it's not crazy. It's just unlucky, right? It's basically a 1 in 6 chance. It's like rolling a die and getting a 1. Are you shocked when you roll a die and you get a 1? Because that's the same chance. It's essentially 17%. No, I'm just saying. Oh, I guess it depends what you're doing. If it's like, that's my golf score for today, then that would be great, right? But anyways, the point is that I break controllers when I roll 1 in Mario Party. I don't know what this means. What is going on? You guys say weird things sometimes. Anyways, Carly, if I missed welcoming you here to the meeting, it's good to have you. But anyways, so the p-value essentially is telling you how likely the occurrence is if the null hypothesis is true. So when would I reject a null hypothesis? For a big p-value or a small p-value?
Big p-value.
Just the opposite. Big p-values are when I do not reject the null hypothesis. Remember, the p-value is how likely the outcome is if the null hypothesis is true. If it's a very likely outcome that if the null hypothesis is true, then why would I reject it? It's only if it's an unlikely outcome, if the null hypothesis is true, that I would reject it. So what is considered a big p-value? That's a great question. So again, 17%? No, not 50%. Usually the rule of thumb is 5%. Anything above a 5% chance of occurring is not considered unusual. It might be unlikely, but it's not unusual. So the general rule of thumb is if the p-value is bigger than 0.05, then we do not reject the null hypothesis. And if the p-value, basically a 1 in 20, that's right. If something has a 1 in 20 chance of occurring and it occurs, that's the border between crazy and just unlucky. Well, so yeah, so what about 6%? Again, you come into the problem in advance and you make your benchmark. You say, my cutoff's going to be 5%. And then you take your sample and you see what your p-value is. If your p-value is less than 5%, you reject the null hypothesis. If it's not less than 5%, you do not reject the null hypothesis. Someone else could come into the same problem and say, my cutoff's 10%. And they would have different rejection or non-rejection regions than you based upon their choice of their cutoff point. But that's their choice. Okay, the less confident you want to be or the more confident you want to be is going to affect your cutoff point, as we're going to see rigorously as we go through the chapter and the coming chapters. Okay, so what we have here, the rule of thumb is 5%, just like 95%. So if a 1 in 20 chance means a null hypothesis should be, if you get an outcome whose likelihood is less than 1 in 20, that's when you reject the null hypothesis. If you get an outcome whose likelihood is more than 1 in 20, you do not reject the null hypothesis. As a benchmark, different problems are going to have different cutoffs. I'm giving you the general rule of a 5% p-value. If the p-value is less than 5%, we reject the null hypothesis. If it's greater than 5%, we do not reject the null hypothesis. Different problems are going to have different cutoffs. In this case, my p-value is 17%. Because it's 17%, no, there's not going to be questions that give, well, there could be questions that want you to compare what you would do with different cutoffs. Like if you have a 5% cutoff, what would you do? If you have a 10% cutoff, what would you do? But there's not a question where you get to decide the cutoff and therefore then make a decision. Every problem will tell you what the cutoff is or how to compute the cutoff. You don't have to worry about figuring it out yourself. So this is just an intro. So they probably don't tell me the details here. Let's see. So think of it like this. So let's look at it from a different perspective. If the null hypothesis is really true, Remember, it comes from a normal. That was one of our assumptions. So we have a normal curve. If the null hypothesis is really true, the center of the distribution should be 0, right? Because they're telling me that, remember, the null hypothesis was mu equals 0. If the null hypothesis is true, we get a value of here mu equals 0, correct? Now, if we get, now remember, this is a sample distribution. So the spread is not sigma. The spread is sigma over the square root of n. So sigma is really 0.316, which means our value of 0.3 is just less than 1 standard deviation away from the mean. Agreed? So if we get a value here, based upon this picture, is that really a crazy value to get based upon this picture? Remember, the center is the most likely, it's the highest. The wings are very unlikely because they're very low. And basically the likelihood of an event increases as you get closer to the center. Would you say that 0.3 is a really unlikely outcome? It's within 1 deviation, right? Most of the data is going to be within 1 deviation. In fact, a third of the data is going to be outside of 1 deviation, right? So getting 0.3 is not a crazy possibility, even when the null hypothesis were true. Now, if I took a much larger sample, I know that my distribution will get very skinny. The same 0.3 for a sample of 100 might have a very different result. Let's take a look. If I change, well, I can't just change it like that, unfortunately, because all my data would change. But let's say, I wonder if there's a way of calculating a hypothesis from here, summarize. Here we go. Suppose I have 100 and I have the same 0.3, same deviation, same mean, same greater than, and I calculate now. So what do you notice about the p-value in this situation?
Smaller.
Much smaller. In fact, what's the likelihood of getting 0.3 for a sample, or even something crazier than 0.3, for a sample of 100 if the null hypothesis were true? It's 1 in 1,000. Now, if something occurred that had a 1 in 1,000 chance of occurring, what would you say to that? Would you say, oh, okay, well, yeah, okay, I can see that? Or would you say, I really seriously need to question whether the null hypothesis is true or not? Jamar, you wrote on my page. How do you do that?
I honestly clicked the little pencil by accident.
That's fine. I didn't know you can do that. That's all. Okay, now everyone's doing it. Great. Open the floodgates.
I'm sorry.
That's okay. That way people can. Oh, but this is awesome now. When I say what's the answer, you can write your own answer. That's okay. Don't just do that. That's just scribble. But what the hell is that? What did he write? I don't even know. Okay, but this is awesome. God, this is like mind blowing. This is amazing. Okay. Anyways, so if something occurred that in 1 in 1,000, you would be absolutely stunned. The p-value is so small that we seriously need to question the validity of the null hypothesis. This is the idea of hypothesis testing. If your mathematical result is so small as to say, I really can't see this happening if the null hypothesis were true, then we would reject the null hypothesis. And if your result is such that you say, okay, it's not what I would necessarily have expected, but it's certainly a reasonable outcome, that's when we do not reject the null hypothesis. That's when the p-value is bigger. That's a general idea of hypothesis testing. Okay? So, in every example, the first thing you're going to do is you're going to state your hypotheses. Okay? We abbreviate the null hypothesis as H0 and the alternative hypothesis as HA. So this book uses HA. You'll see H1 in books. You'll see HA in other books. A for alternative, or 0, 1 for the initial and the other one. It doesn't really make a difference. I don't care which one you use. I'm familiar with both of them. The hypothesis always refers to the population parameter. You will never, ever, under any circumstances, have an X bar in these two sentences. Okay, these two sentences are about what the population mean is equal to or not equal to. This happens before you even take a sample. So that your X bar, your sample mean, is something that comes after the fact. Okay, I have an hypothesis. I want to test my hypothesis. So I will take a sample. But your hypothesis and what you want to test are decided before you take your sample. They're there already in advance. In this case, it's a one-sided alternative hypothesis because it's greater than. If it's two-sided, it means it's different. So what's an example of different? Suppose, to use the example that they did, but a little different, Coca-Cola comes out with their 2-liter bottles and puts the 2-liter bottles in production. And they probably want to have some quality control to make sure that it's not less than 2 liters on average, and it's not greater than 2 liters on average. Because remember, it's never going to be exactly 2 liters in any bottle. It might be, within a 0.00001. I mean, I don't, whatever their precision is, but it's never going to be exactly 2 liters. Some are going to be more, some are going to be less. Why would Coca-Cola not want to have an average of more than 2 liters in a 2-liter bottle? What is the negative effect on the Coca-Cola company if they have on average more than 2 liters per bottle?
They lose profit.
They lose profit, right? They lose profit because this is all money that this is all Coke that they could have put in a new bottle. Then I don't know. Someone asked, is the process used more with companies often or is more used for third-party quality control? I don't have an answer for that. I would assume that most large corporations have internal quality control. That would be my assumption, but I just don't know. I don't have an answer for you. But whether they hire from without or whether it's from within, either way, they don't want to have too much Coke in the bottles because then they lose profit. Why would they not want to have too little Coke in the bottles as well? Why would that be a problem? I would think they can make even more profit that way. Why would
lose customers?
Well, they might lose customers. Customers will be angry. Customers could sue, right? If I buy 2 liters, I expect 2 liters. So there's a reason in that case why they don't want to have too much and they don't want to have too little. So in that case, my alternative will be two-sided. Is it 12 or is it, is it 2 liters or is it not equal to 2 liters? So sometimes we're curious, is it greater? Sometimes we're curious if it's less. Sometimes it's two-sided. We're curious if it's different. Every example, it'll be obvious or there'll be enough information for you to figure it out. So like this example here, does job satisfaction of assembly workers differ when their work is machine-paced rather than self-paced? Differ. Is it different? They don't say, is it better or worse? They say, is it different? So this will be a two-sided hypothesis test. Okay, does that make sense so far? So the subway used stats to get away with giving out, so I don't have an answer for you. It could be that they didn't expect anyone to notice, but in today's day and age, everyone notices everything. It could be that the original bread was 12 inches, but then when it's cooked, it shrinks to the point where it's no longer 12. I don't know. I just remember reading an article about it, so that's why I thought of the example. I don't even know if they ended up with 11.5. I don't really remember the article. I'm sure you can Google search it, but I just don't remember the details. And I don't know what happened after that. I don't know what the subway's response was, whether they actually were sued, and if they were, what the outcome was. This will be a good report. All right, so next, p-value and statistical significance. So, so let's first do p-value because I already brought it up. So ignore the first paragraph in this box and go to the second paragraph. The probability computed assuming that H0 is true. Okay, well, I guess they talked about the test statistics. So ignore what I just said. Let's start here. A test statistic calculated from the sample data measures how far the data diverge from what we would expect if the null hypothesis were true. In the last example, we had an H0, a null hypothesis. We said we believe that mu should be equal to 0. Our test statistic in this case was the sample mean, whose value was 0.3. Do you mean potato chips?
Yes.
Why? Oh, because of all the air in the bag?
Yes.
Yeah, that's a, you know what I just bought yesterday or 2 days ago? Oh, whatever. I bought like a box of Jay's hot stuffed potato chips, like this much, because I'm starting my diet in like 2 weeks. So I have to get it all in now before my diet starts, because that's how you do a diet, right? You put on 20 pounds a week before the diet, so you can lose a lot right when the diet starts, and you feel very good about yourself. Anyway, that's my philosophy. But either way, yes, we should sue them, or at least calculate. Okay, that's just gross. That's just the most disgusting thing I've ever seen. I'm not eating a tapeworm. Okay. Anyways, let's keep going. So a test statistic calculated from the sample data measures how far the dropped 50 pounds in 2 days. Okay, maybe it's worth it. But anyways, a test statistic calculated from the sample data measures how far the data diverge from what we would expect if the null hypothesis were true. If the null hypothesis is true, this is what we would expect. Your test statistic is what you actually got. Unusually large values of the statistic show that the data are not consistent with the null hypothesis, right? Unusually large. 0.3, I'm not sure if that's unusually large or not. 117 is most likely unusually large. The probability computed assuming that the null hypothesis is true, that the test statistic would take a value as extreme or more extreme than actually observed, is called the p-value. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. So if I look at my normal distribution, if the null hypothesis is true, I expect 0 to be right in the center. My value is here. I got 0.3. What I compute is the likelihood of getting what I got or something even more extreme. The probability of landing in this region, which we know how to do from a few chapters ago, that's the p-value. The p-value is the probability of getting what I got or something even more extreme, something even further away from my null hypothesis value. That we can get on Crunch It, on the calculator, online. We have multiple means. Okay, does that make sense? Again, these couple chapters on confidence intervals and hypothesis testing are just the basics. They're giving you an idea of what we're doing. And then what's going to happen is we're going to get into the nitty gritty and really do lots of examples of all the different formulas and do lots of situations. This is just the basics. And in fact, it's 5:30. So why don't we just stop here before we go any further? So I can go eat some tapeworms or something. Are there any questions on what we've done so far? I'm disgusting. Gross. You're a disgusting human being. All right, so if there's no other questions, I will see everyone on Tuesday, and I will have your tests and everything graded by then because, of course, I took roll. I'm always taking roll. I will add you as being late, and Carly, you as well. And Carly, stick around for a minute, please, actually. And I'm going to stop recording so I can minimize this. What was the name of the chips that you brought? You want to see? I'll show you. Let me stop recording first.